I would like to emphasize also, because I have seen that most of you have actually not a computational simulation background, so that the examples are preliminary from our own background, but most of you are experimentalists, experimental researchers. So that's why I would also like to indicate the same thing can be and is already also done, not that extensively yet, I have to admit, but we have good examples also for experimental processes. So these are slides from my colleague at BAM, Özlem Özcan, who is an expert in self-driving lab technology and materials acceleration platforms, where you try to synthesize materials based on an inventory of chemical errors. You have you analyze this, you evaluate your analysis, and have this as a feedback loop. And so this also is a process of different steps that you need to execute. And of course, you can also at the end describe every step with a Python function, which somehow steers your machine. And you need to combine these functions, and you need to combine the data, the analysis data are necessary in order to design the next step with some Bayesian optimization, for instance. Yeah, and so one example is this kind of multi-electrode connected to a multi-electrode analyzer. So that's a photo from the lab. It allows you to have different drops on a wafer with different electrochemical conditions, and then to execute this automatically. So for the different drops, you have to different kind of descriptors for the electrochemical behavior. I am not an electrochemist. I cannot comment on all details, but yeah, that's the kind of Python-based screenshot. You have your parameters to run your electrochemical experiment. You have this saver, and you have then this optimization loop in order to handle these kind of electrochemical profiles where you then want to optimize certain parameters. That's the experimental side. When we think about combining simulation and experiment, so this also this mission or vision I've put at in the first part. We would like to make use of the knowledge graph of data, enrich them by workflows, but also benefit with workflows from the knowledge graph. Then there's here one example for this. I've taken this now from the more academic world of NFDI Mathwerk, but I think it's a nice representation of what we have in mind. So we have, on the one hand, experimental data. So transmission electron microscopy gives you very nice results on how grain boundaries are decorated by other elements. You have the simulated data. So I come back to this segregation of elements to grain boundaries, which we can calculate with density function theory. And then you have perhaps further analysis steps. We have a lot of groups involved here in this joint collaborative project. But important is if you describe the data from both sources, experiment and theory, based on the same ontologies. So yes, for instance, here a domain ontology, which is for this crystallographic defect, and then use this kind of conceptual dictionaries in JSON format to exchange this data. So one way is then to handle a knowledge graph is to represent information in an electronic lab notebook combined with a storage solution. Then this is a way of getting this kind of benefit of semantic description for making different approaches interoperable. Let me quickly go through how this looks in practice without having time to go into material science here. But the typical data are experiment, as I mentioned, transmission electron microscopy, high angular dark field microscopy is here on the right-hand side. And this is a typical atomic structure which we use for simulations for such a grain boundary here. So they are actually, for this structure in magnesium, there are two different even flavors of this grain boundary, and we would like to see which flavor, which structure is stable under which conditions. And this performance of the grain boundary is connected to the alloying, and the alloying is connected to the mechanical behavior of magnesium. So pure magnesium is very brittle. You would like to alloy the magnesium with other elements in order to improve your stability, and one way is grain boundary engineering. So you would like to understand your defect. You would like to run simulations for the segregation to this defect, and you do this with this high-end quantum mechanical calculations, density function theory. But once you know what are the relevant configurations, you do it a high throughput study with a more efficient tool, which allows to use these machine learning potentials I've formerly mentioned. And then you have a code for generating phase diagrams, and you put it into your framework for representing your knowledge graph, your structured data. OpenBIS is one of the electronic lab notebook solutions. And that's what we do. We get the data inside. Very quickly, material science is then for different atomic configurations. We get different energies. It's the formation energy of the grain boundary for different chemical configurations. You can collect this in this kind of diagrams. It tells you under which gallium content in this case you have what kind of configuration stable. And this is our map of possible scenarios. And we combine this now with the knowledge from experiment. Yeah, so we have all the setup to allow that what we do with workflows is in a proper way semantically annotated. We do this inclusion then into the knowledge graph or whatever kind of structured data format we use based on the ontologies, and the PMD core ontology will extensively be introduced to you next week. And we need also the application ontologies like the one for the defects. And having done it this way, then we can also retrieve the experimental data, just described then with in the same way. We can make from simulation side, from the Python workflow, some kind of query, get experimental data sets, and then can use our map of computed data to connect it with the relevant experimental structures, and in this way translate this general diagram into a specific diagram for these experimentally observed structures. Unfortunately, no time for the material science, but I hope you understood the concepts. Having the semantic enrichment of workflows, and that means also of the data generated by workflows, allows you to interoperably combine results from completely different sources.